Hello, I'm Shumpei Shiina, a student at the University of Tokyo. Today I'm going to introduce our paper, Lightweight Preemptive User-Level Threats, which investigates preemption techniques for user-level threats. Let me first describe the motivation of this work. In various situations, more threads than the number of cores are created. For example, if a parallel program calls some external libraries and the library is also parallelized, there is nested parallelism. In addition, asynchronous tasks can be created dynamically, and they are often represented as threads. So efficient thread schedulers for handling these many threads are needed. Today, software stacks of applications are often complicated, and many parallel libraries are hierarchically composed, yielding nested parallelism. Also, in complicated situations like in set analysis, various kinds of tasks coexist, and creating many threads. Therefore, it is important for the thread schedulers to be able to efficiently handle many and fine-grained threads, so lightweight thread implementations are required. In addition, customizing thread schedulers for specific workloads is often beneficial, because though general thread schedulers do not perform well in some situations, it is important to design thread schedulers for specific workloads by utilizing some application hints. For example, locality-aware scheduling for memory-bound applications and priority-based scheduling have been intensively studied until now. This example shows a priority-based scheduling with work stealing strategy. Like this, the user can freely define complex scheduling policies, and it is desirable for the application programmer to customize thread schedulers for their own needs, especially for complicated softwares. Inset analysis is a good example in which high priority threads and low priority threads coexist, and high throughput of computation is important. And in this work, we will focus on the end-to-end threads or user-level threads, which are lightweight and flexible thread implementation. One-to-one threads or kernel-level threads are threads controlled by the OS kernel. In one-to-one threads, one thread visible to the user is directly mapped to one kernel-level thread. Okay, however, the one-to-one threads are insufficient for thread scheduling for high performance because of their heavyweight threading operations such as thread creation and context switching. They are heavyweight because they involve context switching to the kernel space, which consumes many CPU cycles. The scheduling policy of one-to-one threads is also inflexible because the user cannot customize thread scheduling policies in user space. On the other hand, end-to-end threads are promising because of their lightweight threading operations and flexible scheduling policies. In end-to-end threads, many user-visible threads are created, and they are dynamically mapped to kernel-level threads. However, end-to-end threads have some downsides. One capability that end-to-end threads are missing is preemption. Lack of preemption can be problematic in many situations. For example, priority of threads can be ignored without preemption. The figure shows that a low priority thread is occupying this core for a very long time, and high priority threads are waiting for it. In this situation, the thread scheduler has no way to remove the lower priority thread from the core unless the thread voluntarily yields the core. If the thread scheduler has a capability of preemption, the lower priority thread can be immediately evicted from the core once high priority threads become ready to run. Another issue caused by lack of preemption is the deadlock issue. The problem is that many existing multi-threaded programs assume that they can exclusively use all of the cores, and thus they sometimes have their own synchronization mechanisms, such as thread barriers based on busy loops or spinning. When they run over non-preemptive end-to-end threads, and there are more threads than the number of cores, a deadlock occurs. In this figure, these threads are waiting for other threads in busy loops, but the thread scheduler does not have a chance to schedule other threads because running threads are spinning on the cores. if we have preemption, the deadlock issue would be resolved. And here is a summary of contributions of this paper. First, we investigated preemption techniques for end-to-end threads, which can be implemented in a pure threading library so that they can be used from C or C++. Specifically, we investigated two preemption techniques. Signal yield is an existing technique, but we found it was insufficient, so we proposed KLT switching for safe preemption. We also proposed several optimizations for preemptive end-to-end threads based on detailed performance analysis. Finally, we implemented preemptive end-to-end threads on AlgoBots, a lightweight end-to-end threading library developed at Argonne National Laboratory. And we evaluated the performance on various benchmarks and applications. And as a result of evaluation, we found that preemptive end-to-end threads can be as fast as non-preemptive end-to-end threads in practical settings. Then I briefly explained two preemption techniques, signal yield and KLT switching. The idea of signal yield is to interrupt execution of threads by a signal issued by some system calls and yield in the signal handler. It is an existing technique proposed in some papers. However, it is not safe for some existing library functions such as glibc-malloc, which depend on the KLT local data or thread local storage. Thus, we proposed KLT switching to realize safe preemption for end-to-end threads. It resolves the KLT dependence issue in signal yield by switching to another KLT only when preemption happens, so that KLT local data are not modified while being preempted. By doing so, more kernel-level threads than the number of cores can be dynamically created, and the cost of KLT switching is much higher than that of signal yield, but it covers a wider range of programs because it is safe. Then I will summarize the thread implementations, and we addressed 4 thread implementations: one-to-one threads, non-preemptive end-to-end threads, preemptive end-to-end threads based on signal yield, and preemptive end-to-end threads with KLT switching. First of all, explicit threading operations such as thread creation and synchronization among threads are heavyweight on one-to-one threads, whereas end-to-end threads have lightweight threading operations regardless of whether they are preemptive or not. The absolute overhead of preemption of end-to-end thread is larger than one-to-one threads, and the cost of KLT switching is much higher than that of signal yield. All of the end-to-end threads have the capability of customizing thread schedulers, and signal yield is not a safe preemption. One downside of KLT switching is its high overhead of preemption, but it is acceptable because preemption is infrequent enough in practice. As evaluation, we measured the overhead of preemption. The figure shows the additional overhead relative to the baseline execution of non-preemptive end-to-end threads. We changed the timer intervals, which are shown in x-axis. First of all, the overhead of KLT switching is improved after applying several optimizations, and the overhead of KLT switching is still much larger than that of signal yield. But we consider the overhead of KLT switching is acceptable. When the timer interval is 1 millisecond, the overhead of KLT switching is only about 1%. And considering that the OS preemption interval is typically in the millisecond range, the overhead of KLT switching is less than 1% in practical settings. From this result, it is found that preemptive end-to-end threads are as lightweight as non-preemptive end-to-end threads in practical settings. And here is the conclusion. We have investigated 2 preemption techniques for end-to-end threads, signal yield and KLT switching. And we also implemented these preemption techniques on AlgoBots and evaluated their performance. We confirmed that preemptive end-to-end threads are as fast as non-preemptive end-to-end threads in practice. And summarizing, the preemption brings more freedom to end-to-end threads in implementing efficient user-defined schedulers with low overheads. Thank you for listening.